So guys, um, so how do we go about doing this kind of question? So to just to remind you, we were told that initial moles initially initially we had x moles. Um, we have x moles of what? Of N2O4 gas. Um, So it was placed in a volume. So we are given volume to be 2 decimeter cube. So yeah. So when equilibrium was reached, okay, it was found that 20% of the N2O2 had decomposed. So at equilibrium, at equilibrium. Note that in the exam you have to structure your problem in this way so that you don't miss any information. So at equilibrium, 20% of of N2O2 gas, O4, I mean O4 gas had had reacted acted had reacted. So so if the equilibrium constant, the question is saying that, so if the equilibrium constant Kc for the reaction is 0.16, so we are given Kc to be 0.16. So calculate the value of x. So they want us to calculate this value. So this value is what they are looking for. So we are calculating the number of moles of Na2O4 initially. So how do we do this problem? How do we do this kind of problem? Because if akuphumanga inakhuza ucase nje straightforward ukuthi you are given initial moles, then you are required to find Kc. If that Kc had not come out, so this one will come out. They will just give you Kc and then they will require you the initial moles. So you can just play around this table of Kc. So what you do, you say rice rice rice. So you say rice. So ngiyazi ukuthi khona bayibuzayo ukuthi lo rice umele niki, so kulula rice. So lo rice lo umele ukuthi ratio initial mole change and equilibrium and equilibrium. So if you look at your reaction there, if you look at your reaction, you will see that you have one there and you have two here. So if you want to write your ratios here, you must take your ratios there. It's just the coefficients, of of the reacting species or of the participating species. So it's the coefficient. So for this one we have 1, and for this one we have 2. So let me separate my table very well. Yeah. So initial moles, are we given the initial moles for this one? No. So just write here in 204, and I will write 2 n2. Yes, so we are not having any initial mole for this one, so we are having x. So are we having initial moles of this one? No, because it's a product and you are not told ukuthi they started with certain products, because in some cases you may be starting with some products in a reactor. So you must consider this as a number. You will not write this as 0, but in this case, in the case where you are not told what amount of product are we starting with, so you just put 0 here always. But if you are told that you are starting with this much of product, then you will have to put that number here. So ebese siyaku-change. So uma siyaku-change, these are the change. This is the change that is observed, because sifaka ini ama-moles ethu initially kwi-beaker or noma kwi-syringe, because sikhuluma nge-syringe. So sifaka ama-moles ethu kwi-syringe, then at equilibrium we observed that there's something left for this one and there's something left for this one at equilibrium. So we are now trying to find ukuthi shuthi kwenzeka ushintsho olungakanani la. Mawukuthi la bengena u1 sekuno2, ushintsho shuthi uba, yabo, into kanjalo. So ake si-check-ke at equilibrium. We are told that there is 20%. We are told that there is 20% of this that actually reacted. So the whole 20% of this X has reacted. So the 20% of this X is the one that has reacted. So the remaining part is the initial moles minus the reacted one. So that reacted one, we put it here. So 0.2 x, we put 0.2 because you just divide that by 100 and you get 0.2, and then you multiply that by to find the percentage of this. So the reason why sifaka la ku-change is because ilama moles vele a-reactile lawa, yabo. So ilama moles a-reactile lawa. So njengamanje sesizothola-ke ukuthi at equilibrium kuzoba uba. So at equilibrium okusho ukuthi kuzoba ilo minus laba ba-reactile, kusala lokho esisale nakho-ke ku-equilibrium. So x minus 0.2 x, this is what we will have here at equilibrium. For the product, remember that NO2 is there just because we have this one. So if this one has reacted complete, it means then we will be no longer forming any of NO2. So the amount of this one that is reacted can be related to an amount of this one that is formed. So using our mole ratio, we can find how much of this are we forming, because this one is formed just because we have this one in the system. So therefore you can basically see from the reaction that if we put 1 mole of this one in the system, we will produce 2 moles of this one in the system. So therefore this is 1:1, this is 1:2, then you will just multiply by 2 to find the moles of this one that will be present in the products. So the easy way that I usually do when I was doing grade 12, I would just say 1 at 2, 1 at 2. So this one is for this one. So I'm having this one which have reacted, and I don't know what is the value of this one in the product. So I would just cross multiply like this, and then 1 times y. 1 times y is 1. So 0.2 multiplied by 2. So you can punch your calculator there and see what you get. 0.2 multiplied by 0.2 multiplied by 2 is 0.4. So it's 0.4 x. So it's 0.4 x. So in the product we will have what we call 0.4 x at equilibrium, and the change because we had 0, so the change is equal to equilibrium value because we had 0 here. But if we didn't have 0 here, then it would be another case. So 4x, then you put plus here showing that you are adding the reactants keep on growing, the product keep on growing in the system, but the reactants keep on decreasing in the system, so you put minus there. So from this step now, because these are number of moles, and the formula for Kc says that Kc is equal to concentration of products over concentration of reactants. So these square brackets mean concentration. So here, if I mark your paper, I would give you a mark that you know a definition of a equilibrium constant. So from here is a substitution. So substitution, your product is NaO2. So your product is NaO2. So I'm looking for a concentration. Okay, now I'm looking for a concentration of NaO2, and then the coefficient becomes your exponent over the reactant is N2O4, and we want the concentration, and the coefficient is 1, so it becomes an exponent here. So it's just like that. So from here, because this one is concentration and these are the number of moles, so you must use the formula which says C is equal to V over C is equal to N over V. I'm sorry about that. So C is equal to N over V. So N being the number of moles and V is the reaction volume, is the area in which the reaction is proceeding. So we were given there that the syringe is of 2 decimeter cube. So we have our volume. We've just basically listed our data there because we wanted things to be easy for us. So you must also do that in your exam. So your number of moles of NaO2, your number of mole of NO2 is this one. So these are the number of mole of NO2, 0.4 V, 0.4 x, 0.4 x over V, proceeding in a volume of 2 over. So you just punch your calculator, 0.4 over 2 is giving you 0.2. So 0.2 x, that's your concentration of what? Of NO2 now. So, and then you will use this formula again to find the concentration of what now? N2O4, and then C is equal to N over V is equal to N2O2. So the number of moles for N2O4 are these ones. So you will put, basically this one is 1 minus it's just 1 minus 0.2, so you can just say 1 minus 0.2, 0.8, so 0.8x, 0.8x, that one is just 0.8x over the volume is 2 over, so 0.8 divided by 2, we get 0.4x. Then these are your concentration now. This is the concentration for this one, and this one is the concentration for that one. So therefore now you can put your round bracket, because you are substituting, you can put your round bracket. So this is the concentration for that one, and this one is the concentration for that one there. So it's the concentration for that one. So you can just you can just substitute 0.4. No, remember that in the top we are having this one, so this is the concentration that we need to use in the top. So 0.2 x x squared, because we had squared here, over round bracket 0.4 x not squared now. So yeah, so therefore Kc is equal to this. Therefore Kc is equal to, if you punch this in the calculator, 0.2 squared, it should be 0.04 x squared over, remember the algebra, can't explain the algebra in physics. We are doing physics here, not mathematics. So, and we're having 0.4 x in the bottom here. So you can see that the x can cancel there. So this x can cancel that one, and the numbers can actually divide. So 0.04 over 0.4 is your answer is 0.1. So this Kc is actually equal to 0.1 x, is 0.1x, so 0.1x. So remember that we were given the value of Kc at the top there. We listed our data, so the value of Kc is 0.16, 0.16, the value of Kc. Therefore 0.16 is equal to 0.1 x. I'm taking it from here, so you can just divide 0.1, whoosh, and x will be 0.16 over 0.1. This is 1.6. You have to write the units, moles. So that's how you approach these kinds of problems.